So in the last class we discussed about Rutherford Woolf-Foyle experiment, and we discussed the scattering phenomena, and also we uh, explained the relation between the number of scattered alpha particle and scattering angle, number of scattered alpha particle with the kinetic energy of the alpha particle, incoming alpha particles, etc. Okay. And in this section, we will discuss two more parameters in the same section, which is the distance of closest approach and the impact parameter. Okay. These two uh, parameters we will discuss. One is distance of closest approach and impact parameter. Okay. So let us again consider the scenario of Gold-Foyle experiment or any scattering experiment, alpha scattering experiment. So if we are considering alpha, so some alpha source here, so these alpha particles are coming and interacting with the nucleus. So some of the alpha particles which are passing very close to nucleus, they will scatter, okay, with some scattering angle. I have denoted scattering angle theta here. So these alpha particles will be scattered with the scattering angle of theta, as you can see from here. Okay, and those alpha particles which are coming or which are passing through some area which is not having any influence of nucleus, which will be passing through the atom. They will be undeflected. So if the alpha particles are passing very far from the nucleus, then they will be undeflected. So most of the alpha particles will be undeflected and they will be just passing through the atom. Okay, these things we discussed in the last class. And some few alpha particles, very few alpha particles will be going through the center, or they will be interacting with the nucleus. We call it as a head-to-head collision because these alpha particles will be interacting with the nucleus at the center. Okay. So they will be deflected back with 180 degree of scattering angle, or the angle between them, angle of the incident alpha particles and the scattered alpha particles will be 180 degree. So they will just come back in the same path, almost in the same path. Okay. So this is called as head-to-head collision. Now let us look at the head-to-head collision again. Let us consider the nucleus here, and the alpha particles are coming from this side. Okay, alpha particles are coming from this side, and when this alpha particles having less kinetic energy, then they will be coming here, and because these alpha particles are positively charged and the nucleus is also positively charged, so since they have positive charge, there will be Coulombic repulsive force for this between these two. So this alpha particle, when they come with some kinetic energy, let's say this alpha particle is having kinetic energy Ke1, and if they are coming close to this nucleus, then there will be repulsive force because they are having same charges. So they can come up to this point, maximum this point, and they will go back. Okay, once they reach this point, then they will go back like this. Okay, for kinetic energy Ke1, because this when it reaches here, the repulsive force will be larger than the kinetic energy of the alpha particle. Then this nucleus will reflect, or they will because of that repulsive force, the alpha particles will come back. But the if you consider a higher kinetic energy, let us consider Ke2, and Ke2 is larger than Ke1. Now, if you consider Ke2 as the kinetic energy of the alpha particle, then those alpha particles can go further a little more as compared to the previous case. Then it can go up to this, okay, let's say up to this and come back. Then it will come back. So if you increase the kinetic energy, the alpha particles will approach very close to the nucleus, or if the kinetic energy is less, then the alpha particles cannot go very close to the nucleus because of the repulsive force. Okay, so with a given kinetic energy, how much the alpha particle can go up to that nucleus, or we can say the distance between the alpha particle and the nucleus, or the minimum distance between the alpha particle and the nucleus with a given kinetic energy in the head-to-head collision. That distance we call it as distance of closest approach, okay, with a given kinetic energy. So if you consider the center of the nucleus here, and from that center what will be the distance for a given kinetic energy, what will be the minimum distance the between the alpha particle and the nucleus. This is called as the distance of closest approach. We call it as R0. Okay, R0. So where R0 is the distance of closest approach. So that is the text given here. That is the same. So the incoming alpha particles has the charge 2e. As you know, alpha particles are having 2 protons, so there will be having 2e charge. And nucleus has charge Ze because they are having Z number of protons. And when this alpha particle is approaching towards the nucleus at the center, and a distance called closest approach distance, the kinetic energy of alpha particle and potential energy of those alpha particles becomes same. Okay. So when you consider the potential energy, potential energy is nothing but if you consider the in terms of force, we can consider it as the Coulombic repulsive force. Positive charges repulse each other, and because of that, we'll be having potential energy. Okay, that corresponding to that force. So that potential energy you can write it as, let's say, U equal to 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0. The charge between the charge of this particle, so that is 2e into Ze, q1 q2 by r, that is the potential energy form. So the distance is r0, that is the minimum distance the alpha particle between the alpha particle and nucleus. So 1 by 4 pi epsilon 0 2e into Ze divided by r0, that is the potential energy. Okay. We are talking about potential energy. If you are considering force, then it is 1 by 4 pi epsilon 0 2e into Ze by r square. Okay, r0 square at that point. So at this point, when it is r0, okay, you can, in general, you can write this as this for any distance. For any distance, it will be r. 1 by 4 pi epsilon 0 is 2e into Ze divided by r. And when it is at the closest approach, this will become r0. When it is at closest approach, distance of closest approach, then this will become r0. And at that moment, what will happen? This alpha particle will be coming to this, and it will be stopped because of that repulsive force, and all those kinetic energy will be equal to that potential energy that is equal to this 1 by 4 pi epsilon 0 2e into Ze by r. So when these two are equal, then the alpha particle will be staying at this point. Okay, it will not be moving for a fraction of a second, and then it will come back. So when the kinetic energy of the alpha particle, incoming alpha particles, equal to the potential energy of in between this alpha particle and nucleus, or the potential energy of the alpha particle, then at that distance will be at that moment the distance will be the distance of closest approach, or you can also say at the distance of closest approach, the potential energy of the alpha particle will be equal to the kinetic energy of alpha particle, or all the kinetic energy will be converted into potential energy at that point. So at r0 we can write all the kinetic energy of alpha particle, that is k alpha, will be equal to 1 by 4 pi epsilon 0 2z into e square. 2z e square you can see from here, 2 into z into e square. Then by r0. R0 is the distance of closest approach, and from that expression we can derive this r0 expression for r0. So closest approach distance, that is r0, will be equal to R0 will be equal to 2z E square by kinetic energy of alpha particle. 2z E square, 2z E square by kinetic energy of alpha particle. You can see. Okay, we will be having this constant also. So 4 pi 2z E square by kinetic energy of alpha particle with that constant. Okay, 1 by 4 pi epsilon 0 also will be there. 1 by 4 pi epsilon 0. Okay, so that is the expression for distance of closest approach. And let us consider an example. If you consider a kinetic energy of if you consider an alpha particle of kinetic energy K alpha equal to 5.5 mega electron volt, and which is 8.8 into 10 raised to minus 13 joule. And if you are considering such a case, which means that kinetic energy of alpha particle is this much, 8.8 into 10 raised to minus 13 joule. And if you are considering gold nucleus or gold foil experiment, and the gold will be having atomic number of 79, and if you substitute all other values, you can see 9 into 10 raised to 9 is 1 by 4 pi epsilon 0. And if you substitute all those values here, E square you can substitute 1.6 into 10 raised to minus 9. So if you are having an alpha particle of this much of kinetic energy with the nucleus as or if we consider gold foil experiments itself, then the nucleus will be the nucleus of gold, and which is having atomic number of 79, that is here. And if you substitute all those values, then you will get what the closest approach in that case, R0 will be equal to, R0 is 4.13 into 10 raised to minus 14, or 41.3. This is 41.3 femtometer. Femtometer is nothing but into 10 raised to minus 15 meter. Okay. So in this way, you can calculate what is the closest approach of alpha particle given with given kinetic energy. Now we will also consider the other parameter, which is impact parameter, and the impact parameter is nothing but the minimum distance from the center of nucleus where the alpha particle can get deflected or scattered. Alpha particle can get deflected or scattered. Okay, that is the impact parameter. So the impact parameter will be different for the given situation, for the given alpha particle with some kinetic energy. So this impact parameter you can see here, this is it is represented as B, small letter B, and the distance is, I will just okay, so the distance you can see from here, this is the impact parameter, this distance from the center of the nucleus to that trajectory, okay, where the alpha particles can get deflected. The alpha particles can. So if we consider another alpha particle which is coming in a different with different kinetic energy, and then you can also calculate what is the impact parameter corresponding to that case. So if you consider that distance impact parameter, then you can write it as the expression for impact parameter and scattering angle. The expression will be like 2b by r0. R0 is the distance of closest approach. This is equal to 2b by r0 equal to cot theta by 2. Then this theta is scattering angle. Then you can derive expression for impact parameter here. The impact parameter b equal to r0 by 2 cot theta by 2. R0 by 2 cot theta by 2. That is the expression for impact parameters, and impact parameter, if you substitute R0 from the previous expression, then you can write it as 2z e square by k alpha cot theta by 2. We will also having that 1 by 4 pi epsilon 0 here, 1 by 4 pi epsilon 0, 2z e square by k alpha. I think yeah, this 2 will get cancelled, right? Because you are having a 2 here. Yes, you are having 2z e square here, so we will be having one more 2 in the denominator, or you can just write it as 1 by 4 pi epsilon 0 or 1 by 8 pi epsilon 0, or you can just cancel this. So it is nothing but 1 by 4 pi epsilon 0 z e square by k alpha cot theta by 2. That is the expression for impact parameter. Okay, we will consider one more example for the case of distance of closest approach. Another example. So in this example, we will consider protons of, this is the example, protons of 1 mega electron volt, 1 mega electron volt energy, scattered with gold nucleus, which means that the same experiment, okay, the Rutherford gold foil experiment, if you are using protons instead of alpha particle, protons are also having positive charges, so they will also get deflected. In that case, what will be the distance of closest approach? What will be the distance of closest approach? That is question. So same expression, you will be having R0 equal to 1 by 4 pi epsilon 0, that is 9 into 10 raised to 9. Then you will be having 2 times z e square, so that is this into 2 into z is 79, e square is 1.6 into 10 raised to minus 19 square. Okay, so all these things are same, divided by the energy will be different. In the previous case, we are having, I think we have different energy, 5.5 mega electron, 5.5 mega electrons. So instead of that, we will be having energy of 1 mega electron volt. Here you substitute that here in joules, okay, in joules, then you will be getting the answer. At the same time, also you can do this example, and you can calculate what will be the or you can compare. If you are considering 1 mega electron volt with alpha particles, you can compare what will be the sorry, this case we will be having, instead of 2 we will be having 1 here, because we are having 1 proton, right? We are not considering alpha particle. Okay, now the expression is right, I think. So 9 into 10 raised to 9, 1 into 79.6 into 10 raised to minus 90 square. Only that 1 mega electron volt, that you had to convert into joules. Then we will just do that part here. So when you convert that into joules, then you will be having that 1 mega electron volt equal to 1.6 into 10 raised to minus 13 joule, 10 raised to minus 13 joules. So just substitute that value, all those values, then you will get R0. This is equal to, if you calculate this expression, then it is coming around 11.4 into 10 raised to minus 14. Just check this much of meter, or you can say this as 114 into 10 raised to minus 15 meter or this is equal to 114 femtometer. So now just do the same with in this case, if you consider instead of 5.5 mega electron volt, if you consider 1 mega electron volt, what will be the closest approach? If you consider that and compare what will be the closest approach, how it will vary with alpha particle and proton. One is heavy particle, alpha particles are heavy particle compared to protons. Then you can get an idea how they will interact, how much close it can go when you consider lighter particle as compared to the heavier particle. Okay, that you do as homework. So that's all about this video, and also you can check these relations also. You can see here the impact parameter here, which is inversely proportional to the kinetic energy of the alpha particle, first thing, and also it is directly proportional to the scattering angle theta or cot theta by 2. We have to specify that cot theta by 2. It is proportional to cot theta by 2. Also, it is proportional to the z atomic number. Okay. So you can practice some more examples with this embed parameter also. So all this will be just substituting the values in the expression and finding out what will be the embed parameter or the distance of closest approach.